For this question, we're going to use logarithmic differentiation to find the derivative dy dx, where y is equal to the square root of x squared minus 100 over x squared plus 100. We do have a restriction on our variable x. It needs to be greater than 10. So when we use logarithmic differentiation, what we're going to do is introduce a log into the equation so that calculating the derivative is a little bit easier. So we're going to take the natural log on the left-hand side and take the natural log on the right-hand side. I'm going to go ahead and rewrite the right-hand side as I do that. I'm going to change that square root to the 1/2 power. X squared minus 100 over x squared plus 100, now to the 1/2 power instead of the square root. Now the reason we're introducing the log is because the log has properties that allow us to expand it so that we have individual terms that are less complicated to take the derivative. So we're going to use some algebra properties of the logarithm to expand this. The first property we're using is going to be the power rule for logarithms. Remember, this is an algebra property, and the power rule for logarithms allows us to take this power and move it to the coefficient. So that would give us natural log of y equals 1/2 natural log of x squared minus 100 over x squared plus 100. Okay, so the next property that we're going to use is called the quotient rule for logarithms. I'm going to use that property because I have a quotient inside the log. So the quotient rule allows us to expand the logarithm into log of the numerator over log of the denominator. So this will give us natural log of x squared minus 100 minus natural log of x squared plus 100. I'll distribute that 1/2 to both logs to get natural log y equals 1/2 natural log of x squared minus 100 minus 1/2 natural log of x squared plus 100. So now that I've used these properties of logarithms, I have some individual terms, and I'm going to calculate the derivative. However, we've taken this equation, which was originally in an explicit format, and now it's in an implicit format. Explicit is when you have y equals. If your equation doesn't have y equals or one variable in terms of the other variable, then we need to use implicit differentiation. I'm going to calculate the derivative with respect to x on the left, giving natural log of y. I'm going to calculate the derivative with respect to x on 1/2 natural log of x squared minus 100 minus 1/2 natural log of x squared plus 100. Now all of these terms have log in them, so we're going to use the derivative rule for logarithms. Derivative with respect to x of natural log of u is u prime over u. So on the left-hand side, the derivative of natural log of y will be y prime over y. 1/2 is a constant multiple. I'll carry that down. We have natural log of x squared minus 100. So do u prime, the derivative of the inside, is 2x over the inside, which is x squared minus 100. 1/2 is a constant multiple, and I'll take the derivative using that natural log rule. The derivative of x squared plus 100 is 2x over the inside of x squared plus 100. So I'm going to do some cleaning up. These 2's cancel. And I have y prime over y equals x over x squared minus 100 minus x over x squared plus 100. I'm going to clean up the right-hand side by combining these into a single fraction. So I need to get a common denominator. So I'm going to multiply on the first term the other denominator of x squared plus 100, x squared plus 100 over x squared plus 100. For the second term, I'm going to do the same. I want to multiply by the other denominator, x squared minus 100 over x squared minus 100. So this will give me a common denominator on the right-hand side, a common denominator of x squared minus 100 times x squared plus 100. In the numerator, I'll distribute those x's to have x cubed plus 100x minus x cubed plus 100x. I distributed this x as well as the negative, which is how I got those signs. So in the numerator, the x cubes cancel, and the 100x and 100x combine to be 200x over our common denominator of x squared minus 100 times x squared plus 100. So now that I've combined that right-hand side into a single fraction, I'm going to solve for my y prime by multiplying by y on both sides. So this will give y prime equals 200x over x squared minus 100 times x squared plus 100. And if you'll recall, y is the original equation that we were given. So let me just move back up for a second there to see what that is. That is square root of x squared minus 100 over x squared plus 100. We can substitute that in for y. So y is square root of x squared plus 100 over x squared minus 100. I might have that backwards. Let me just double check that one more time. The plus is in the denominator. Okay. All right, so we have a minus 100 in the numerator and a plus 100 in the denominator. So we have here our derivative. I'm going to do just a little bit more cleanup to see if I can combine some things together. What I notice is that I have a base here of x squared plus 100 and another x squared plus 100, so I'd like to try to combine those together. And then I also have an x squared minus 100, and I'd like to try to combine those together. So I can try to write this as the 1/2 power again, and I'll write this as x squared minus 100 over x squared plus 100 to the 1/2 power. And then I can apply that power to the numerator and denominator separately. So I have 200x over x squared minus 100, x squared plus 100, and times x squared minus 100 to the 1/2 over x squared plus 100 to the 1/2. So now that I've got these two bases separated, I can combine them with the other base that's the same. Now, the first one we'll look at here has one base in the numerator and one base in the denominator. So we're going to use a property of exponents called the quotient rule for exponents. And this is a property, this is an algebra property of exponents. So we use it if we have base b to the m over base b to the n. If we're dividing with the same base, we subtract the exponents to simplify. So this will give us b to the m minus n. So this exponent is to the 1/2 power, and this exponent is to the 1st power. If I want to combine those together, I'm going to do 1/2 minus 1, which is negative 1/2. So this will be the new exponent on x squared minus 100. When you do that new exponent, that base is in the numerator. So I'm going to get rid of that negative by moving that base to the denominator. So that will give me the x squared minus 100 to the 1/2 power in the denominator. So I changed it to a positive 1/2 by moving that base to the denominator. That's a property of negative exponents. So this is what the property looks like. If you have b to the negative m, I can write that as 1 over b to the m. So I applied that negative by moving that base to the denominator. Okay, so let's focus on the other. The other base is x squared plus 100, and those are both in the denominator. So we're going to use the product rule for exponents. And the product rule for exponents looks like this. If you have b to the m times b to the n, this is where you are multiplying with the same base. That's why it's called the product rule. And this is also an algebra property. And when you multiply with the same base, you're going to add the exponents, m plus n. So our new base, x squared plus 100, we're going to have the same base of x squared plus 100, but we're going to change the exponent. So we have an exponent of 1 and an exponent of 1/2. So 1 plus 1/2 is going to be 3/2. That's going to be the new exponent. Now, this base is in the numerator, this base is in the numerator, the answer is in the numerator. we started off with our base in the denominator, and the new base is in the denominator. So this gives us our final answer, 200x over, I'm going to turn it back into radicals, square root of x squared minus 100, and the square root of x squared plus 100, and this one's to the third power. I have another question with logarithmic differentiation to calculate the derivative dy dx. And this time our equation is y equals 5 plus x to the 3 over x. And once again, we have a restriction on our variable x. X needs to be greater than 0. And this is usually because we're introducing the logs, and logs have a domain. Log x has a domain of x being greater than 0. You can only take the log of positive numbers. So we're going to introduce the log to simplify the expression on the right so that it's easier to calculate the derivative. So we're going to do the natural log on the left and the natural log on the right. Okay, once we introduce those logs, we're allowed to use the log properties. We're going to use the power rule for logarithms to take this exponent of 3 over x into the coefficient. We have natural log of y equals 3 over x times natural log of 5 plus x. So from here, we're going to calculate the derivative, and we started off with an equation that is in explicit form. We have one variable written in terms of the other variable, y equals. And once we introduce the logs, we've now changed the equation into an implicit format. So in that implicit format, we need to, when we calculate the derivative, we're going to use implicit differentiation. So calculate the derivative with respect to x on the left, and calculate the derivative with respect to x on the right. So I have 3 over x, natural log of 5 plus x. So we're going to be using the derivative of logs, that rule for the derivative of natural log. Derivative of natural log of u is u prime over u. So the derivative with respect to x of natural log of y, is y prime over y. The derivative of the inside here, the derivative of y, these variables don't match, so that's why we just write that y prime. Whereas on the other side of the equation, we have a variable of x, and we're taking the derivative with respect to x, so we will be able to calculate the derivative. Now, on the right-hand side, we're taking the derivative of 3 over x times natural log of 5 plus x. So I'm going to have to use the product rule to calculate this derivative. And I'm also going to think of 3 over x as 3x to the negative 1. So I'm going to use the power rule when I'm calculating that derivative. So using the product rule, I'm going to do the first factor of 3 over x times the derivative of the second factor. The derivative of natural log of 5 plus x, that will be 1 over 5 plus x, following that natural log derivative pattern. So we've got the first factor, times the derivative of the second factor plus the second factor natural log of 5 plus x times the derivative of the first factor. So I'm doing the derivative of 3 times x to the negative 1. 3 is a constant multiple. I'll use the power rule. That's negative 1 times x to the negative 2. So we bring that power down and take 1 away from the power. So here we have calculated the derivative. Let's do a little bit of cleaning up. We have y prime over y, 3 over x times 5 plus x, plus, now let's make that a minus. I'm making it a minus because I have a plus here, times 3 times a negative, so positive times the negative will be a negative. It'll be minus natural log of 5 plus x. We can put a 3 here. And then the x squared, I'll move that down to the denominator to get rid of the negative in the exponent. So now what I want to do is to combine the right-hand side into a single fraction. So I'm noticing that I have a factor of x here and a factor of x squared on the other term. So I need to multiply by 1 factor of x so that I can have x squared on this first term. I'm going to multiply by x over x to get x squared on the first term. For the second term, I'm missing the 5 plus x. So I'm going to multiply by 5 plus x over 5 plus x to get what I'm missing. And if I clean that up, I'll have 3x over x squared times 5 plus x minus 3 times 5 plus x natural log of 5 plus x over x squared times 5 plus x. You can write that as a single fraction, and that will give me x squared times 5 plus x, 3x minus 3 times 5 plus x, natural log of 5 plus x. Continuing, I want to isolate the y prime. I'll do that by multiplying by y on both sides. Now, if you remember, y was given in the original equation to be y was 5 plus x to the 3 over x. So I'll substitute that in. We have y equals 5 plus x to the 3 over x times that fraction that we got, 3x minus 3 times 5 plus x, natural log of 5 plus x, over x squared times 5 plus x. And this is probably where I would stop with my simplification on this problem. We could possibly combine these two together, but it doesn't really provide with a much simpler looking expression. I'll go ahead and do it just so we see what it looks like. Here we are dividing with the same base, so I would use the quotient rule. With the quotient rule for exponents, you subtract the exponents, so you would do 3 over x minus 1. 3 over x minus 1 would be 3 over x minus x over x. That's 3 minus x over x. So we would have 5 plus x to the 3 minus x over x times 3x minus 3 times 5 plus x, natural log of 5 plus x over x squared. That doesn't really clean it up that much. So here's where I would stop. For this question, we want to use logarithmic differentiation to find the derivative dy dx on the equation y equals x times square root of x squared plus 5. We do have a restriction on the domain of x is greater than 0. So we want to introduce the log. The log will help us simplify the expression on the right so that we won't have as many derivative rules to consider. We're going to calculate the derivative. Right now we're doing the log. We're going to take the log on the left and take the log on the right. I'll go ahead and I'll rewrite this radical as a power. That's x squared plus 5 to the 1/2 power. Now introducing the log allows us to use the log properties to expand this logarithm. So on the right we have a product inside the log, x times x squared plus 5 to the 1/2. So I'm going to use the algebra property for logarithms, the product rule. That'll give me natural log of x plus natural log of x squared plus 5 to the 1/2 power. I have one more property of logarithms I can use. I have this exponent, and there's a power rule for logarithms which allows me to move this power to the coefficient. I'll have natural log of y equals natural log of x plus 1/2 natural log of x squared plus 5 to the, we got rid of that 1/2 power. Okay, so now that we've used those log properties, I want to use implicit differentiation to calculate the derivative. We're using implicit differentiation because we started off with an equation that's in explicit format, but by taking the log of both sides, we've changed that equation to an implicit equation. So because our equation is implicit, we're going to use implicit differentiation. So I'm going to calculate the derivative with respect to x on the left and do the same thing on the right, the derivative with respect to x. So on the left-hand side, I'm calculating the derivative with respect to x, and the variable is y. This is a mismatch of variables. So I don't know what y is, so I can't really specify what the derivative of y is, other than to write the symbols y prime. We have y prime over y, using the derivative rule for natural log. The derivative rule for natural log is derivative with respect to x of natural log of u is u prime over u. Now on the right-hand side, we're taking the derivative with respect to x, and the variables used are x, and so we will be able to calculate the derivative. So the derivative of natural log of x is going to be 1. That's the derivative of x is 1 over x, the inside. 1/2 is a constant multiple, and we'll calculate the derivative of natural log of x squared plus 5. The derivative of x squared plus 5 is 2x over the inside x squared plus 5. You can clean this up just a little bit by canceling out the 2's here. I have y prime over y equals 1 over x plus x over x squared plus 5. On the right-hand side, I'm going to combine these fractions into one fraction by getting a common denominator. So the first term, I'll multiply by x squared plus 5 over x squared plus 5. The second term, I'll multiply by x over x. This will give me the common denominator of x times x squared plus 5. So that common denominator will be x times x squared plus 5. And in the numerator, 1 times x squared plus 5 is x squared plus 5. And x times x is x squared. We have 2x squared plus 5 over x times x squared plus 5. And on the right, I still have y prime over y. I do want to solve for y prime. That was the goal. Y prime is dy dx. I'll multiply by y on both sides. And recall that y is x times the square root of x squared plus 5. I'll make that substitution. 2x squared plus 5 over x times x squared plus 5 times x times square root of x squared plus 5. Now the x's will cancel here. And I do have these two factors with the same base. I want to combine them together. So I'm going to use some of our exponent properties. When you have the same base and you're dividing, you simplify by subtracting the exponents. So we have x squared plus 5 to the 1/2 power over x squared plus 5. This is to the first power. They have the same base and they're being divided. So to simplify, we subtract the exponents. So we would have the base of x squared plus 5, 1/2 minus 1. That's x squared plus 5 to the negative 1/2. And I don't want to write it with a negative in the exponent. So I'll write that as 1 over x squared plus 5 to the 1/2 power. So these two combine together to be this right here. That's 2x squared plus 5 over the square root of x squared plus 5. I'll turn that 1/2 power back into the radical. So we have our derivative y prime or dy dx being 2x squared plus 5 over square root of x squared plus 5. In this example, we are going to use logarithmic differentiation to find dy dx. We're going to do that logarithmic differentiation on the equation y equals x to the x minus 3. And we're restricting the domain to be x is greater than 0. So we're going to introduce the log so that we can calculate the derivative of the right-hand side. So natural log of y equals natural log of x to the x minus 3. So introducing that log allows me to use one of the properties of logarithms called the power rule. So I'm going to take this exponent of x minus 3 and move it to the coefficient. That's the power rule for logarithms. It's an algebra property. So we have x minus 3 times natural log of x. We have natural log of y. I'll go ahead and distribute that x so that we have x natural log x minus 3 natural log of x. So now that we've simplified the expression, we're going to calculate the derivative. We'll calculate the derivative with respect to x on the left. This is the process of implicit differentiation. We're going to calculate the derivative with respect to x on the right as well. We're using implicit differentiation because our equation is now in an implicit format. Implicit is when you don't have one variable in terms of the other. This is an example of the opposite of implicit, which is explicit. So this equation does have one variable in terms of the other. Y equals, and all the variables on the right-hand side are x. So that's one variable in terms of the other. Okay, continuing with our process, we're using implicit differentiation. We're taking the derivative with respect to x on both sides. So the derivative of natural log of y, following the natural log rule, will be y prime over y. On the right-hand side, for this term, I'll need to use the product rule because I have x times natural log of x. So x is the first factor times the derivative of natural log. It's 1 over x plus the second factor of natural log x times the derivative of the first factor. Derivative of x is 1. Then I need to take the derivative of 3 natural log of x. The minus 3 is a constant multiple. I'll carry that down. And the derivative of natural log x is 1 over x. So let's clean this up a little bit. We've got some x's canceling, and we have y prime over y equals 1 plus natural log of x minus 3 over x. So I'll get a common denominator. So I'll change the 1 to x over x. The natural log of x, multiply that by x over x. And I don't need to multiply by anything on the last term. So now I have a common denominator. That would give me x plus x natural log of x minus 3 over x. And I want to solve for y prime. I'm multiplying by y on both sides. This is y prime over y equals, and remember y was given to us to be x to the x minus 3. So I substituted that original y into the equation. So we have x plus x natural log x minus 3 over x. The last thing that I'm going to do to simplify will be to combine these two because they have the same base. And we combine them, excuse me, I apologize, over here these y's cancel. So I don't have this y in the bottom here. It's y prime equals x to the x minus 3 times x plus x ln x minus 3 over x. Okay, so going back to where we are, these two have the same base and I want to combine them. They're being divided, so I'm going to use the quotient rule. And in the quotient rule, we simplify by subtracting the exponents. So this one has an exponent of 1, x minus 3, x minus 3 minus 1 is what we use to combine those. We have x plus x ln x minus 3. And that will give us x to the x minus 4 times x plus x ln x minus 3. So that's our y prime, or dy dx. Derivative of y with respect to x.